Hello and welcome to the 2021 ELECOMP Virtual Summit. We are Team Acumentrics FaultLine, and this is our project on the SmartPDU 1 Fault Detection Unit Integration. Our technical directors for this project are Brendan Smirbeck, an incredibly talented software engineer. He is the Assistant Program Director for ELECOMP and former Capstone Designer for Acumentrics ASA from the class of 2017. Mike Magellani, a PCB extraordinaire, also credited for being a former Capstone designer. Mike worked on the network-managed power distribution system, known today as the SmartPDU 1 from the class of 2018. Bill Owens, Acumentrics Vice President of Engineering with more than 25 years of experience in quality systems manufacturing. And Najib Ishaq, Consulting Technical Director and Data Science Prodigy. Najib's knowledge and experience with machine learning and data processing proved to be invaluable in the success of Project FaultLine. The designers that worked on Project FaultLine include myself, electrical engineers Anna Skelly and Mackenzie Sherlock, and computer engineer Oscar Ramirez. Founded in 1994, Acumentrics has since become a dependable and accredited market leader in rugged, uninterruptible power supplies, with a wide customer base ranging from large defense contractors to the American Armed Forces. For the last 27 years, Acumentrics has worked to provide clean power conditioning and battery backup technology through both hardware and software solutions. The motivation for this project stems from the idea of predictive maintenance. The premise is to monitor the performance of an operating appliance to reduce the likelihood of failures or faults. This is done with prior knowledge of what these faults entail, which is obtained through non-intrusively monitoring the power signatures of both working and faulty devices. However, why stop at one appliance? We wanted to take this incredible progress that last year's team made and integrate it into a power distribution unit from the year before. My team and I set out on a mission to expand this premise across 8 outlets, taking charge on the next generation of power management and monitoring. And that's exactly what we did. I'm proud to say Team FaultLine has achieved our anticipated best outcome of FDU and SmartPDU integration. The team was also tasked with the additional outcome of configuring the fault detection unit to incorporate 3-phase power and an extended best outcome to design and build loads for calibration, which was primarily handled by our electrical engineers. In order for one to build, one must understand the tools they are working with. This began with understanding the Raspberry Pi used in the FDU, the NVIDIA Jetson Nano used in the PDU, and the Ubuntu Linux distribution used across both computing platforms. Additionally, the team needed to grasp important electrical concepts like the AC power triangle, non-intrusive load monitoring, and 3-phase power. Next, we learned the necessary machine learning components like collecting and grooming data, training models using this data, and finally, performing inference or outcome prediction using a trained model. The team configured a new FDU board for single phase as well, and at the time of recording, the board remains untested. The economic implication for this product is to adhere to a growing market for predictive maintenance across all industries. This is done through how the product is designed to function. The PDU's main priority is to increase the longevity and usefulness of appliances. This increased longevity has the capability to save companies thousands, if not millions, of dollars in revenue, otherwise spent on replacements, repairs, and most importantly, time. Ultimately, this product aims to attract new customers while ensuring the satisfaction of those we currently serve. The map you see on your screen is an overview of the steps required to achieve our first anticipated best outcome, beginning with the reproduction of last year's progress, then moving towards modifications with regards to how data is acquired, and the machine learning model. Next, we discuss performing inference on multiple fans at once before finally casting the results to our webpage. My contributions to this project involve changing how the data is stored on the PDU, collecting data on the PDU, modifying the machine learning model, documentation of performance accuracy, and performing inference using multiple fans at once. This is the project pipeline describing how data flows throughout the PDU. It begins with the initialization of our integrated circuit before verifying a response. After a response has been verified, we collect and clean our data before performing a prediction and casting the output. Going more in depth on collection, we first note a change in the IC. Last year's Team FaultLine chose to use Analog Devices ADE 7880. The chip was selected for a number of reasons, most notably for its ability to perform harmonic analysis. And while this analysis proved quite useful in their prototype, it lacked the ability to analyze more than 3 appliances at once. The ADE 7816, while incapable of harmonic analysis, makes up for this loss with 6-channel input for analyzing currents, and thus was chosen to be a worthy replacement. The second major factor in collection is the change in how we store the data. Before modification, data on the SmartPDU was being stored to a Postgres database. In order to use the collected data to train our model, we modified the output to store a file using comma-separated values. The architecture we used in training our model is a long, short-term memory recurrent neural network, due to its ability to learn from time series data and extract both short-term and long-term features. We built our model using Keras API for TensorFlow. We chose Keras because it is both beginner-friendly and easy to be read by humans. The model was trained using the NVIDIA GeForce RTX 2060 Super graphics card, which resulted in much faster training times than traditional CPU training. What you're watching on your screen right now is a video demonstration of live inference being cast to the web page. The first fan I turn on is a working appliance. The corresponding outlet on the page turns green to let the user know the fan is in good condition. The second fan I turn on is faulty. It has coins attached to one of its blades, forcing the fan's motor to use more energy, thus replicating a fault. As a result, we see this fan's corresponding outlet on the page turn red. I'll now hand it over to Oscar, who will cover the web page and the software side of anticipated best outcome number 2.
So for my individual technical contributions this semester, I mainly focused on working on the previous team's code on the FDU for data collection, so I could collect 3-phase power data from the fans. I was also in charge of creating a web application that has been integrated with the live inferencing script that displays the output results onto a web page. So for the creation of the web application, I used a Python library called Streamlit. Streamlit is an open source Python library that makes custom web apps for machine learning and data science, and it was the way to go for the web app for this project. Currently, the web application reads the results that are generated by the live inference script. The live inference script creates results every second, so the web application is set up to read those results every second. Now let's take a look at the web application. Here you can see fans 1 through 8 being displayed, and it will display either if it's a bad fan or a good fan, depending on what the results say from the live inference script. As you can see, there's also a stop button if you want to stop live inferencing, and it'll stop. Now, let's talk about 3-phase. 3-phase. Mainly for 3-phase on the software side, I had to go back and look at the datasheet for the ADE 7880 chip and see what was missing. With the help of one of my Capstone teammates, Mackenzie, we were able to figure out what was missing and what was needed to be added to the code to collect 3-phase data. You can see a portion of what was missing on the registers list to the side here. Last year's team mainly focused on phase A, so we had to go back and add phase B and C to make sure that it can collect 3-phase data. After that was done, I had to test the collection script by collecting fan data and to see if the CSV that was being generated had 3-phase data. To my success, the CSV that was being generated had 3-phase power data. And why the success of collecting 3-phase power data is important, it sets up the next team who works on this project for polyphase power data collection. And for more on that, I introduce my Capstone teammate, Mackenzie Sherlock.
So, let's recap. With the previous year's FDU now implemented into the PDU, ABO1 was achieved, making Project FaultLine a success. But, as with every success, there's always the eventual question that's never too far behind. Where do we go from here? The answer? Maintaining project momentum. With ABO1 completed, electrical engineers Anna and I identified 2 paths to ensure that Project FaultLine success can keep going, even beyond the end of Capstone year. These paths are developing a polyphase FDU and Designing PDU Calibration Loads, which both serve as the project's ABO2 and Extended Best Outcome, or EBO. The following were my contributions towards completing ABO2 and the EBO. Among them, highlights include drafting documentation for communication with the FDU's power monitoring chip, designing the calibration loads, and assisting in data collection for the Polyphase FDU. Now, moving forward, I will be talking about how we upgraded the previous year's board from single-phase to polyphase data collection. Although last year's FDU board design had eventual polyphase power monitoring in mind, it couldn't be actualized due to time constraints. We are happy to report that we were able to finish setup of the Polyphase FDU by returning to datasheets of the ADE 7880 chip and its evaluation board. This let us select the anti-aliasing circuitry we needed by modifying jumper configurations, whose differences can be seen here. Then, for future FDU boards, we also updated the PCB design for a better fuse layout than is displayed here. This is the Polyphase FDU fully assembled. Since more phases meant more inputs, we also completed the additional wiring needed to support polyphase data collection, shown here. So what does the Polyphase FDU mean for Acumentrics? The Polyphase FDU's impact lies in two key areas. It addresses difficult debugging needs as well as expands Acumentrics clientele. Firstly, debugging a single-phase power appliance is already difficult. There's a lot of data to review, from looking at average and waveform voltage and current to a device's differing harmonics. Polyphase adds another degree of difficulty with each additional phase, making collecting the increased amount of data even more integral in diagnosing the faults. Secondly, single-phase power is generally only used in residential and company environments. Commercial and industry, on the other hand, need polyphase to satisfy the machinery's high power requirements, which can assist in these other applications. Because of these potential benefits, it is no wonder our technical director informed us that Acumentrics is already receiving inquiries about smart energy monitoring that supports polyphase power, making the Polyphase FDU the next step in helping Acumentrics smart power monitoring products to be more desirable to more people. Next up is Anna, who will be talking about what we made to enhance the PDU as it is, right now, the calibration loads.
Thank you, Mackenzie. While a three-phase version of the FDU looks to the future, having a calibration loads for the SmartPDU is a practical solution for calibration. Just like a piano needs to be tuned to sound good, the SmartPDU needs loads to calibrate it in order to ensure accuracy. This semester, the electrical engineers on the team completed their part of the ABO fairly early and decided to work on an extended best outcome. We decided to design and build calibration loads. So we have RL and RC circuits, and we were given a few specifications. We were given the current, the voltage, and the power factor we wanted. So these loads are good for calibrating because we know exactly what we have, and we need to make sure that the PDU reads what we have on the circuit. So there are three loads that were needed. There was the low power RC load, the low power RL load, and the high power RL load. So in order to design these circuits, we utilized a new concept for us, which is the power triangle. This triangle is used in everyday engineering for power. It is a highly used thing. So this was a new topic that we got to learn and utilize. So the design process was we had to find the apparent power from the current and the voltage, then the real power from the apparent power and the power factor that we had, then the reactive power, and then from there we could find the resistance that we wanted and the capacitance that we needed. So yes, and from there we got three circuit designs. We have a low power RC circuit which uses 600 ohms and 2.55 microfarads. We have a low power RL circuit which uses 120 ohms and 0.54 henries. And we have a high power RL circuit which uses 4 ohms and 0.018 henries. Because these values are not common resistor or capacitor or inductor values, we had to do some math and figure out configurations that would work for us. So for the RC circuit, we ended up using 4 capacitors, 4 2 microfarad capacitors in series and a capacitor in parallel with that in order to get the correct value. And then we had that in series with resistors. For the low power RL load, We put 3 inductors in series and then had that in series with the resistor we wanted. Unfortunately, for the high power RL circuit, it gave us a lot of really weird results when we were testing it. The inductors we originally bought were giving us the value that was about a fourth of what it said it should be, so we were not unsure. And in order to utilize what we had, instead of buying more things, we decided to use half of a power transformer that was custom built for Acumentrics. And a power transformer is basically 2 inductors next to each other. Unfortunately, this power transformer was giving us worse results than the inductors that we had bought, or was just basically not completing the circuit. It was a very weird issue that we unfortunately didn't have enough time to figure out, but we did at least build it, and we're in the process of troubleshooting. So this semester, my individual technical accomplishments were pretty much the same as Mackenzie. The main things I've done this semester was I assisted with the collection of PDU data, and I helped design and I built the calibration loads. So to summarize our anticipated best outcomes and our extended best outcome, our anticipated best outcome we have completed. We have constructed a data pipeline, modified both data acquisition code and machine learning model to train using data from multiple fans. We have successfully inferred in real time using multiple fans at once, and we've displayed these results to the Acumentrics webpage. Our ABO2 we have almost completed. We have configured and built the 3-phase FDU, and we have generated a machine learning model for the FDU and have trained a little bit on it, but unfortunately we didn't have enough time to test it in order to show you guys, so I'm sorry. And then we have the extended best outcome, where we have designed and built 3 RC and RL loads. Unfortunately, we did not get to finish troubleshooting one of the RL loads, but it is built. And so we would like to thank our technical director, Brendan Smurback, for all of his work with us and all of those late nights. We'd like to thank Mike for his help with the FDU design, and we'd like to thank Najib for all of his help with the computer engineers and all of their issues. We'd also like to thank Bill Owens and Dr. Sunak for giving us this great opportunity to work with Acumentrics for our capstone project. Thank you.